Here we will consider some examples for finding the probability density functions of x when the respective characteristic function is given. In the first question, we are given a characteristic function phi t is equal to e raised to minus t square by 2. Based upon this characteristic function, we have to determine the respective probability density function. First of all, we note that this is the characteristic function of standard normal distribution. So the density function we are getting using this corollary of inversion theorem is that must be the density function of standard normal distribution. In order to determine this characteristic function, in order to determine the density function from the characteristic function, we will consider the corollary of inversion theorem, that is known as inversion formula. So according to this corollary, we have if a characteristic function is absolutely integrable and its derivative of capital F of x exists, then the PDF corresponding to capital F of x is given by this 1 by 2 pi integral minus infinity to infinity e raised to minus itx phi of t dt. Actually, this is an inverting technique of finding the density function using the given characteristic function. So this is the equation used for finding the density function from the given characteristic function. And before that, in order to derive this density function from the characteristic function, in this question we have to examine whether this phi t is absolutely integrable, that is modulus phi t is integrable. So the first part is to examine whether this given characteristic function phi t equal to e raised to minus t square is absolutely integrable or not. For that we consider integral minus infinity to infinity modulus phi t dt, and that is equal to integral minus infinity to infinity modulus e raised to minus t square by 2 dt. That is inserting or taking that modulus into the integral, and we are replacing phi t by the respective equation e raised to minus t square by 2, and since it is always a positive function, it is integral minus infinity to infinity e raised to minus t square by 2 dt. And this is a standard integral. We have its value root 2 pi because in standard normal distribution the equation is 1 by root 2 pi e raised to minus t square by 2, and as it is a proper probability distribution, the total integral from minus infinity to infinity must be 1, or the integral side, that is minus infinity to infinity e raised to minus t square by 2 dt, will be equal to root 2 pi. So root 2 pi is a finite quantity, therefore we have this modulus phi t is integrable, or phi t is absolutely integrable. So now we are using the inverting equation of uh, density function from characteristic function. So this is the equation. So we have 1 by 2 pi integral minus infinity to infinity e raised to minus itx into phi t dt. So citing the equation of phi t here, and then doing some simplifications, we get in the 1 by 2 pi integral minus infinity to infinity e raised to minus 1 by 2 into t square plus 2 itx dt. Next, our attempt is to bring a perfect square in the power of this exponential function. For that, we add and subtract an x square. So it is 1 by 2 pi integral minus infinity to infinity e raised to minus 1 by 2 t plus ix whole square into e raised to minus x square by 2. Here we take together t square, then 2itx, and plus minus x square. So minus x square is taken inside. So this plus x square and into minus 1 by 2, that is separated. So that is why this e raised to minus x square by 2. So three terms like t square, 2itx, and minus x square, they were taken together and brought to a perfect square t plus ix whole square, along with the remaining part e raised to minus x square by 2. And so in short, it is 1 by 2 pi e raised to minus x square by 2 integral minus infinity to infinity e raised to minus 1 by 2 t plus ix whole square dt. And it is uh, symmetric about this ix. So we can write it as this twice integral minus ix to infinity is symmetric about minus ix. So it is twice integral minus ix to infinity e raised to minus 1 by 2 t plus ix the whole square. And doing certain simplifications, we can see this twice integral 0 to infinity. That is when we take this u as 1 by 2 t plus ix the whole square. So it will be twice integral 0 to infinity e raised to minus u then root 2 1 by 2 root u du, and that is equal to integral 0 1 by root 2 pi integral e raised to minus x square by 2 and 0 to infinity e raised to minus u then u raised to 1 by 2 minus 1. This is gamma half, which is root pi, and this is a pi here. So when root pi will be cancelled, it is 1 by root 2 pi e raised to minus x square by 2, which is the equation of standard normal distribution. So here we have a step-by-step derivation of this winding density function from the known characteristic function using the inversion formula. So we are not using that comparison of the characteristic function that we do in moment generative function, a sequential process of finding this density function from characteristic function. So the next question is check whether modulus phi t is integrable in the following cases, and if so obtain a PDF by inversion formula. So we have the case of phi t is equal to 1 minus modulus t when modulus t less than 1 and 0 if modulus t greater than or equal to 1. That is the characteristic function. So the aim is to determine the density function having this model of characteristic function. So first of all, we examine whether this phi t is absolutely integrable, that is integral minus infinity to infinity modulus phi t dt. So this is taken as minus infinity to minus 1, then it is 0 because modulus t greater than 1, phi t is 0. Then another section is from minus 1 to 0. So minus 1 to 0 means 1 minus minus t. That second minus t is to have the modulus t. So that 2 minus or 1 plus t, that is our minus 1 to 0, phi t will be modulus of 1 plus t. Then next is 0 to 1 modulus of 1 minus t. That inner modulus t will be positive when this t is between 0 and 1. That's why integral 0 to 1 1 minus t dt. And the last section is 0 1 to infinity, and 1 to infinity this modulus t no, not modulus t, phi t is 0. So in short, the total integral minus infinity to infinity has been taken in 4 different segments. One is from minus infinity to minus 1, and over which phi t is 0. The second section is minus 1 to 0. Over that interval, phi t will be 1 minus minus t, that is 1 plus t. So it is in modulus 1 plus t. And likewise, the next 0 to 1, it is modulus 1 minus t. And the last section is 1 to infinity, and over that interval this phi t is 0. In short, the remaining two intervals are minus 1 to 0 dt and 0 to 1 dt, and both integrals have values 1, so 1 plus 1 2, and it is finite. So which means that modulus phi t is absolutely integrable. So now we be back to the equation of integral inversion formula. There is one f of x equal to 1 by 2 pi integral minus infinity to infinity e raised to minus itx phi t dt. So we substitute the equation of phi t here. So 1 by 2 pi integral minus 1 to 0 e raised to minus itx 1 plus t dt. That is when t lies between minus 1 0, and the second part is t lies between 0 1. Over that interval, phi t will be 1 minus t. So e raised to minus itx 1 minus t dt. Now next we do the integration by parts. So in the first section it is 1 by 2 pi outside as a common factor. Then we consider e raised to minus itx by minus ix, then into 1 plus t, that is by treating this v as e raised to minus itx and u as 1 plus t in that equation of uv, integral uv, that is the product integration by parts. So this is that equation we get using integration by parts. So the two terms for integral minus 1 to 0 e raised to minus itx 1 plus 2 1 plus t dt, and the next two terms are for the integration by parts equation of integral 0 to 1 e raised to minus itx 1 minus t dt. So we sort out the terms and supply the limits. So we have the first half, it is 0, that is 0 upper limit. So this will be 1 by minus 1 by ix and then plus 1 by x square. That is when we cite limit 0 in the section of the first integral, and then upper integral, no sorry, lower limit minus 1. So when lower limit minus 1 is given, this will disappear, and this is e raised to ix by, not ix by x square. Likewise, the second part of the integration, and here the limits are 0, 1, and when the upper limit is given, we get e raised to minus ix by x square and plus 1 by ix, and that's all, e raised to minus ix by x square, and for 0 to 1, the second two terms. So we can simplify this. So these two will cancel each other, 1 by x square, 1 by x square, 2 by x square, then minus 1 by x square, and here this is e raised to ix, that is cos x plus I sin x, and this is cos x minus I sin x. So when we simplify, it will be 1 by pi x square into 1 minus cos x. So this is the PDF corresponding to the characteristic function given, that is phi t is equal to 1 minus modulus t if modulus t less than 1, and 0 if modulus t greater than or equal to 1. That is a second example. Now next is phi t is equal to e raised to minus modulus t. As we know, this is the characteristic function of Cauchy distribution. So based upon this given characteristic function, we can invert its density function, the corresponding density function, and for that we will make use of the inversion formula. So before that, we just examine whether this phi t is absolutely integrable. That is, we consider integral minus infinity to infinity modulus phi t, and we know that it is integral minus infinity to infinity e raised to modulus e raised to minus modulus t. So when we break at 0, that is e raised to minus modulus t, has two segments. One is from minus infinity to 0, and other is 0 to infinity, and both integrals have values 1 and 1. So 1 plus 1, 2 less than infinity. So it is absolutely integrable. So we substitute that characteristic function in the equation of inversion formula, and it is 1 by 2 pi integral minus infinity to infinity e raised to minus itx into e raised to minus modulus t dt. So now we break that total integral from minus infinity to infinity at 0. So we have two segments, one is minus infinity to 0 and 0 to infinity. Our minus infinity to 0, that modulus t is equivalent to minus t, our minus infinity to 0, and our 0 to infinity modulus t will be equivalent to t itself. So therefore e raised to minus itx into e raised to t, our minus infinity to 0, because that e raised to t is because the already existing minus and that another minus of modulus t, so it is e raised to t. Then the second half is 0 to infinity, and the modulus is inactive, that is modulus is same as the value of t, that's why e raised to minus itx into e raised to minus t. So then doing then again some simplifications and integrating, we get this step, and the next step we supply the limits. So when that upper limit is given 1 by 1 minus ix, and nothing happens in the lower limit because everything will disappear, and the other side, then it will disappear because of the upper limit infinity, and will be plus due to two negatives, the one negative already existing in the denominator and also the second negative from the lower limit, so it is 1 by 1 plus ix. So on simplification we get that uh, we get we get 1 by pi into 1 plus x square, which is the Cauchy distribution. Then this is an example of modulus phi t is not integrable, and therefore we cannot find out the density function corresponding to this characteristic function. So this is a characteristic function because it has all the properties of characteristic function, like this phi 0 1, then uniformly continuous, all the properties. So this is a characteristic function, but this characteristic function is not invertible. Invertible because it is not absolutely integrable, and that is verified in this integral minus infinity to infinity modulus phi t dt. We see that uh, it is integral minus infinity to infinity e raised to 3it dt. What is the modulus e raised to 3it? Modulus e raised to 3it is 1 itself because it is root of cos square uh, 3t plus I sine square plus not I plus sine square 3t, that is 1 itself. So it is simply integral minus infinity to infinity dt, and therefore it is infinity, therefore it is not integrable, and so we cannot determine the density function having this characteristic function. Now next example is phi t is equal to e raised to it minus 2t square, e raised to it minus 2t square. Okay, having a close watch on this equation, we find that this is the characteristic function of a normal distribution. That is, the normal distribution characteristic function is e raised to mu t minus t square sigma square by 2. The structure is very much therefore identical to that of a characteristic function of normal distribution. But however, we will have step-by-step derivation of finding this density function from characteristic function using inversion formula. So before that, we will just examine whether it is absolutely integrable, and we can see that integral minus infinity to infinity modulus phi t dt is this integral minus infinity to infinity e raised to it minus 2t square dt. So we see that it is integral minus infinity to infinity e raised to minus 2t square dt. So doing that integration, further we take some transformation, at last we get it as root of pi by 2. It's a very simple transformation, that is transforming to a gamma integral, and that transformation is 2t square equal to u. Doing the subsequent changes, so we get it as root pi by 2, which is finite, so it means that this is absolutely integrable. So again we use that inversion formula. So we have this step 1 by 2 pi integral minus infinity to infinity e raised to it minus 2t square into e raised to minus itx dt. So doing the simplification here, we are inserting some term in order to make that exponential part as a perfect square. Then only we can make it as a symmetric integrand, and so then we can transform easily to a gamma integral. So that's why we are adding and subtracting a term like 1 by 16 into x minus 1 square, and the term to be added and subtracted can be identified by just having a close watch on that terms inside the bracket of exponential, that is e raised to minus 2t square plus it into x minus 1. So when we take 2 outside, it is t square then plus it by 2 x minus 1. So these are the only the first square term and only the second product term. So one more square term is missing, and that second missing square term can be determined just by doing that or comparing with a plus b whole square, and that's how we have 1 by 16 into x minus 1 square, and to balance we again minus 1 by 16 x minus 1 square, and then taking the constant term outside of the integral, that is not term without the t, so we get this Now we have this integral, and that integral is symmetric about t equals 1 by 4 into x minus 1. So that is simply done, integrated by transforming to gamma. So before that we have a twice integral 1 by 4 x minus 1 to infinity. That is using the property of symmetric integral. That is, if a function is symmetric about x equal to a, integral minus infinity to infinity, that integral will be equal to twice integral a to infinity. So that's why we have this point of symmetricity as 1 by 4 into x minus 1. So it is twice integral 1 by 4 into a 1 by 4 into x minus 1 to infinity, and so on. So doing that simplifications to get a standard gamma integral, and we get it as this uh, twice integral 0 to infinity e raised to minus u 1 by root 2 1 by 2 root u du, and this can be treated as a gamma 1 by 2. So on simplification we get it as 1 by 2 root 2 pi e raised to minus 1 by 2 x minus 1 whole square, which is the normal distribution with the mean equals 1 and standard deviation as 2. Standard deviation 2. Run variance 2, that is n mu sigma. N mu is 1 and sigma is 2. So this is the way we are inverting the density function from the characteristic function, and for that we make use of inversion formula. So next is a property of characteristic function, that is the uniqueness theorem of characteristic function. This result is very much familiar to us. It's very much identical to the property of homogeneity function, uniqueness theorem of homogeneity function. And practically we apply this result to find the density function based upon the characteristic function or homogeneity function. That is, by the structural resemblance we can determine the characteristic function of determine the density function when the characteristic function is familiar to us or which is known to us. So that is known as uniqueness theorem of characteristic function. So the statement is a distribution function determines undetermined by its characteristic function. So it has a forward and backward result. One is a distribution function determines its characteristic function, and the second is the characteristic distribution function is determined by its characteristic function. So first we consider f be the distribution function and phi be its characteristic function. So what is phi t? Phi t is the expectation of e raised to I tx. So integral I tx d capital F of x, and we can see that this is a convergent integral because phi t will exist always, because this expectation is finite. Modulus of its expectation of the modulus is finite. So this is uniquely determined. So phi is uniquely determined. So once one distribution function is given, phi is uniquely determined. So never one distribution can have two characteristic function because of this convergence of absolute convergence of this expectation, that is phi t will be existing always, and that's about the forward. Now to prove the converse, suppose that characteristic function phi t is given. So the result is the result required is then corresponding to the given characteristic function phi t, f is unique. That is, f can be determined uniquely by this given characteristic function. So by the inversion theorem, we can determine the characteristic distribution function. That is, using the inversion theorem, once the phi t is given, we can determine the distribution function. The second part of this is to show this f is unique. That is, uh, this is the result. F of a b is equal to limit c to infinity 1 by 2 pi integral minus c to z e raised to minus iat minus e raised to minus ibt phi t dt. Then phi can be always determined. Phi can always determine f. Now next is how to show it is unique. That is, f is uniquely determined. So already we found that it is determined using characteristic function. Now next our attempt is to show it is uniquely determined. And for that we take the contradictory side, that is we assume that there are two distribution functions corresponding to one given characteristic function. That is, we have two distribution functions f and f dash. Means for one characteristic function we have two distribution functions f and f dash, and we will come to the result f and f dash are one and the same, they are same. So as a contradictory side we take there are two distribution functions, one is f and other is f dash. Since both are distribution functions, both distribution functions have the features of distribution function. So that is f of p minus f of a, that is by the inversion formula. So f dash b minus, this is f dash a, not f of a, this must be f dash a. So f dash b minus f dash a is the same thing. So since both are distribution functions, both are determined from characteristic functions using the inversion formula. So f of b minus f of a equals to a right side, and the same right side for f dash b minus f dash a. Sorry, you have to treat this as f dash a, not f dash, no, not f of a. That is f dash b minus f dash a. So since the right sides are equal, we can take the left sides also equal. F of b minus f of a is equal to f dash b minus f dash a. Now, but we have the f of infinity, f dash infinity equal to 1, because both f and f dash are distribution functions, and that f of minus infinity and f dash minus infinity also 0, again since both f and f dash are distribution functions. Now in this result we keep a fixed and take b to infinity. In this left and right side we take a fixed and take b to infinity. So what happens to this? F infinity minus f of a equal to f dash infinity minus f dash a, which means that f of a is equal to f dash a. That means there is no difference in f and f dash as far as the point a. Likewise, when we keep b fixed and take a to minus infinity, we get this. There is a correction. This is f of b is equal to f dash b. F of b is equal to f dash b. Please treat it as f dash b. So it means that f and f dash are equal for all x. Therefore, there is a contradiction to say both f and f dash exist. Since they are equal, it is uniquely determined. So therefore, this characteristic function uniquely determines the distribution function. So the forward and backward part of that statement true. So again I repeat, you have to consider the corrections here. One is here this is f dash b minus f dash a, and the second is uh, f of b is equal to f dash b. I shall do the correction using the pencil in the video, even though it already published in the PDF format. Okay, and this is f dash. So that's about the uniqueness theorem of characteristic function, and that's the end. Okay.